And one noise what you have seen is drain current, and one noise what you now see is gate noise. So gate noise, I told you in the gate side, it is open. So the input impedance of FET is always infinity. So definitely that is going to pick up whatever noise which is available in the gate side. So in addition to drain current noise, you have this additional noise called as gate noise. So this, see, actually, gate side is open. So the resistance of gate is infinity. So ideally, zero current will be flowing through the gate. But because of this presence of noise, some noisy gate current will be flowing through your gate. So ideally, noise current is zero, gate current is zero, but practically this noise current at the gate is not going to be zero. It is going to create some impact in the performance of your MOSFET. So even though at low frequency, the current is very small because current is proportional to the bandwidth, right? So at low frequency, the current is not dominating. But since we are going to operate the FET at a very high frequency, so at high frequencies, this gate noise will also dominate. And this gate noise current is given by this equation, I N G square equal to 4 kT delta Gg into delta F. And this Gg is going to be the conductance given by this value, omega square CGS square by 5G D naught. CGS, it is the gate to source capacitance. Omega is the frequency, and G D naught is the drain conductance of your MOSFET. So it depends on quite a lot of parameters as we see from this equation. It also depends on temperature. It also depends on bandwidth. It also depends on frequency omega. Omega equal to 2 pi f. So if you substitute 2 pi f, this gate noise will also depend on frequency. High frequency operation, the noise will be very high. So you have to have a compromise between how the noise is modeled using different applications. So one scientist, Van der Zeel, he gave a value of 4 by 3 for the gate noise coefficient delta in the long channel devices. So you can see here you have a coefficient called delta, right? So this coefficient delta is called as gate noise coefficient. So by doing this experiment repeatedly in MOSFET, he found that for long channel devices, this delta value was found to be 4 by 3. And you can see how the gate noise is modeled in MOSFET. So you have a noise current flowing. Parallelly, you have a resistance Gg and you have a capacitance CGS. And you can see the other side is open. So this can be the simplified gate noise circuit for MOSFET. So because of this resistance, you will be having the noise current, and because of this capacitance effect, which is predominant at high frequency, everything will come in parallel. Whenever you know you are going to draw a current source, the resistance and all components will try to keep them in shunt. The CGS will not be available at low frequency; it will come only at high frequency because CGS is going to be the stray capacitance, which is becoming very very dominant at the high frequency operation of MOSFET. We can clearly see that in the expression for the gate noise current, it depends on omega. So I cannot say that this noise is going to be constant for all the frequencies. No, it is going to vary with frequency. So that is very clearly evident from the expression for ING square, which is in turn depending on omega. So I cannot clearly say it has a constant spectral density. No, it is going to have a variable spectral density, which is going to vary with temperature, and it is also going to vary with frequency.